Hi all. We have already discussed some portions of our module 5. This module is for registers and its operation as well as for counters. So we have already seen these topics like what is a register. This register can store digital information. It's a unit that can store digital data. And suppose you want to store some n bit of information in a register, we need an n bit register. And how can we implement a register? We can implement register using flip-flops. Sequence of flip-flops. Suppose you want to store a 4-bit information, we need 4 flip-flop in sequence and we need to arrange in a particular order that flip-flop sequence will form a register. And sometimes this register, we can impose some operation over this registers like shifting operation. Left shift and right shift operation. So the register that perform these kind of or register that support these kind of shifting operation is known as shift registers. So based on that mode of shifting, we have different types of register, or we can call it as shift registers. Okay, based on that mode of operation on this registers, we can classify the shift registers into 4 types: serial input, serial output, serial input, parallel output, parallel input, serial output, and parallel input, parallel output shift registers. These are 4 different types of shift registers. Okay, we have already discussed all these diagram of this. These are the block diagram representation for our previous 4 different shift registers. And we have different types of applications for this shift registers. In this, we have already discussed about 2 such shift registers. Based on the application, we know now that a ring counter and switch tail counter or Johnson's counter. Okay, so this ring counter, this will generate a particular pattern, a ring pattern that states that this particular register going to generate that follows certain pattern. Okay, so what is that pattern? This is that diagram, block diagram representation for ring counter. See how can we connect that ring counter circuit. See that the first flip-flop output is connected as an input to second flip-flop, and at the end the last flip-flop Q output or that original output is considered as an input to our first flip-flop. This is the diagram for ring counter. So consider a case, a 4-bit ring counter. 4-bit ring counter means how many flip-flops required? In that ring counter, we need 4 flip-flops in sequence. How can we implement that input connections? For that clock input, we have to choose one external clock pulse and it should be synchronous. Like this. That means the same clock pulse we have to connect with all the 4 flip-flops in a synchronous fashion. Okay, and how to connect that input? Suppose these are D flip-flops. 4 D flip-flops. Okay, so the Q out of first flip-flop has to connect with the input port of our second flip-flop. This Q form the input of next one, this Q form the input of next, and this Q form the input of our first flip-flop. Now this shift register acts as a 4-bit ring counter. Okay, and this will form our final output. These Qs will form our final output. Okay, thus this and this. Okay, so in the first clock pulse, suppose this is our initial state of our flip-flop. Here it is like 0, second flip-flop 0, 0 and 1. This is the initialization case. So after this initialization, suppose we are going to apply that first clock input. Okay, so after that the shifting will happen like this. This one, the last one output moved to shifted to first flip-flop. The previous 0 comes to here, this 0 comes to here, this is shifted to here. Okay, so in the next clock pulse it will shift to next position, and the pattern is like this. Okay, see, after that fourth clock pulse, the same input pattern, see, the same input pattern will repeat. It will start repeating after fourth clock pulse. So from this pattern we can conclude that here we have considered 4 flip-flop ring counter, 4-bit ring counter, right? So in 4-bit ring counter, after fourth clock pulse, it will start repeating the previous pattern. Okay, so from this we can conclude like this. Here we have 4 flip-flop in that ring counter, so it generates 4 different states and it will start repeating. It will start the same pattern again and again after each 4 clock pulses. Okay, so we can generalize this like, for an n flip-flop based ring counter or a n bit ring counter, it will generate n different states, only n different states. See, we know that if we are available with n bits, how many different patterns are possible? 2 raised to n different patterns are possible. But in this ring counter, it won't generate all those 2 to the power n patterns. Among these 2 to the power n patterns, it will generate only n different states based on our initialized value, initialized pattern. Whatever value is initialized here in this 4 flip-flop, based on that it will generate only n different patterns, not all that 2 to the power n patterns. We can generate total 2 to the n, we have, it's a possibility. If n bits are available, we can generate as a maximum 2 to the power n different patterns. These much patterns are possible using n bits. But in ring counter, it will generate only n different patterns based on the initialized condition. This is that application of ring counter. If we want to generate only a particular n different patterns, we can go for a ring counter based on a specific initialization. That is the case of ring counter. Next, this is actually that timing diagram representation of the same shifting, 1-bit shifting in a ring fashion. So next is that slight variation of our ring counter, that is switched tail counter, or we can call it as Johnson's counter. Okay, so this is the case here. Instead of connecting the last Q output as an input to our first flip-flop, you have to connect the Q bar output of your last flip-flop as an input to your first. That is the only variation for this Johnson's counter from ring counter. Okay, you have to connect the Q bar output of your last flip-flop as an input to first flip-flop. So here it is listed. Here again it is considering a 4-bit Johnson's counter. That means here it is using a 4 flip-flops in sequence. See how many different patterns are generated here. Here it generates 8 different patterns and it will repeat after that 8 pattern. That is the case of Johnson's counter. Okay, suppose you are given, here it is number n equal to 4. So if n equal to 4 means 4 different bits or 4 different flip-flops are used in the circuit. So in this total, how many different patterns or states are generated? 8 different states. Means if n equal to 4, it will generate 2n different state and it will repeat after that 2n states. That is the application of Johnson's counter. So we know that in general, if n bits are available, suppose here n equal to 4 bits are available, maximum possibility of different state is 2 to the power n, that is here it is 2 to the power 4, 16. from that 16 different state, it will generate only 2 into 4, 8 different state. 2 into 4, 8 different states. In general, we can say like if n different bits are available, the Johnson counter will generate 2n different state. After that, it will repeat. So here initialized with full of 0. Then it will generate 8 different patterns. Then after that 8 pattern, it will repeat while applying next clock pulse. Okay, so this is the case of Johnson counter. See, here it is the case of 4-bit Johnson counter, initialized with full of 0, and after playing the clock pulse, the inverted QD is 0, its complement form is feedback to first flip-flop. Again, the QD output is 0 here, its complement form is feedback to QA input. So the pattern will be like this. See, after that 8 clock pulse, after generating 8 different patterns, it will start repeating. Okay, so this is the case of Johnson. Ring counter generate n different state and repeat. In Johnson counter or in that switched tail counter, it will generate 2n different state and repeat. This is another application of your shift register. Another application is, this is new for you, this is a linear feedback shift register. LFSR in short. Linear feedback shift register. Here we use that property of XOR gate. Along with your shift register, we have to use XOR gate functionality. So here it is 3-bit linear feedback shift register. So we need 3 flip-flop in sequence with same external clock pulse in a synchronous fashion. And here we can take that output of any 2 flip-flop and taken it as an input of your XOR gate, and its output is connected with your external input to your first flip-flop. We can represent the same in another fashion like this. This is indicating 0th flip-flop, this first and this second flip-flop. Here the first flip-flop output and the 0th flip-flop output and the second flip-flop output is considered as an input to your XOR. Its output is taken or considered as an input to your first flip-flop. This is linear feedback shift register. And what is the property? Here it generates maximum of 2 to the power n minus 1 different state. We know that if we have n different state, it will generate as a maximum 2 to the power n possible different states. But this linear feedback shift register will generate 2 to the power n minus 1 number of different state and will repeat. Okay, suppose n equal to 4. Total possibilities 2 to the power 4, 16 different states. In the 16 different state, a linear feedback shift register will generate 16 minus 1, 15 different state, and it will repeat after this 15 states. And the same, this linear feedback shift register can be represented in terms of polynomial also. This is a common representation for our linear feedback shift register, that is representation in terms of polynomial. Okay, the serial external input is considered as x to the power 0, and see like this, the same representation, and here the final external input to the first flip-flop is considered as x to the power 0. Just assume this x as a delay. So for inputting to this external input as an input to your first flip-flop, that x indicate there is no delay, and in order to transfer that input to your first flip-flop output portion, we need 1 clock pulse delay, that is x to the power 1, indicate a single delay. So the same value, whenever it will come as an output to your second flip-flop, it will come here as an output of your second flip-flop. We need total 2 clock pulse. So after setting an input value here, applying the first clock pulse, that value comes here. after a delay of single clock pulse. That is why this x to the power 1. After a delay of 1 clock pulse, it will come as an output to your first flip-flop. Again applying the second clock pulse, the same value will comes as an output of your second flip-flop. That is why x to the power 2. Delay of delay. After second clock pulse, after a delay, after 2 times delay, the same value comes as an output to your second flip-flop. Then what is the meaning of this x cube? After the third clock pulse or after the third delay, the same previously set value comes as an output to your third flip-flop. That is why x to the power 3. Here it is x to the power 4. That means after the fourth clock pulse or after 4 delay, that initially set value comes as an output to your fourth flip-flop. That is the meaning of this x to the power 1, x square, x cube, x to the power 4. So here S output and T flip-flop output is considered as an input of this XOR, and output of this XOR is connected as an input to this first flip-flop. So in this polynomial representation, x cube and x to the power 4 is considered as input to XOR, and its output is connected to first flip-flop input port. Okay, so this is that polynomial representation corresponding to our previous diagram. X to the power 4 or plus x to the power 3 plus 1. What is the meaning? See, x to the power 3 and x to the power 4 XORed and is connected to this. X to the power 0 means what? This term will always comes with all the polynomial representation. This one indicate that serial input of our first flip-flop. X to the power 0 is equal to 1. Okay, so that is why this particular representation x to the power 4 plus x to the power 3 plus 1. Okay, so this is the different patterns generated by our x to the power 4 or plus x to the power 3 plus 1 this LFSR, linear feedback shift register. What are the possible states? See, initially it is set with full of 1, 1, 1, 1. And what are the states? This one indicate x to the power 1, x square. This is x cube and this is x4, and that input to first flip-flop is represented as x to the power 0. That is equal to what? 1. Okay, so here you have to XOR these terms, x to the power 4 and x to the power 3. See these two. 1 XOR 1. We know the truth table of our XOR. If both the bits are equal, either full of 0 or either 1, 1, output as 0. Okay, so here it is 1, 1. 1 XOR 1 is 0. This will form the input to our first flip-flop. So it is shifted to here. And in the next clock pulse, again, these two XORed, 1 XOR 1. Here again it is 0. That will form our input of first flip-flop. Again, see 1, 1. 0. That 0 form input of our first flip-flop. Next, 0, 1. 0 and 1, different states. So, output of XOR is 1. That 1 forms input of our first flip-flop. So, as a total, it will generate how many different states? 1, 2, 3 up to 15. That is 2 to the power 4 minus 1. 16 minus 1, 15 different states, and after that it will repeat the same pattern. Okay, so here we have one assumption, we have one conclusion, that is a necessary condition for generating maximum length by this linear shift feedback register. Maximum length is what? Here using a linear shift linear feedback shift register, we can generate a maximum of 2 to the power n minus 1 states. These are the maximum possibility of different states by a LFSR. Okay, so in which case, in which situation this maximum states this LFS are going to generate? So these are some necessary condition. What is that? Maximum length is possible if the number of tapes in the given polynomial are even, or the tape number should be relatively prime in a set. These are necessary condition, not the sufficient condition. That means, what is the meaning of this necessary condition? If that LSFR, the given LSFR generating the maximum possible state, then that LFSR should satisfy this condition. So always satisfy such LSFR, always satisfy this condition. The tape numbers are even, or the tape number should be relatively prime in a set. What's this tape number? Number of x terms that indicate tape number. Here we have one x term, another x term. And this particular polynomial generate the maximum number of states. We have already seen here it generate 15 different states, right? So it's generating maximum number of state. Such an LFSR always follow this condition. The number of tapes is always even. Here it is 2 tapes. And the number of tapes in this entire set is relatively prime. That 4 here, the number 3 here. This 4 and 3, and here it is x to the power 0. Okay, we don't need to consider this term 4 and 3. This is relatively prime. So whenever this LFSR generating that maximum number of terms, that LFSR should always contains even number of tapes, or the number associating with the tapes should be relatively prime. And this is not that necessary condition. For example, this is another polynomial that satisfying this condition. How many tapes? 2 tapes, and 3 and 2 are relatively prime. So this satisfying this condition, but this is not the LFSR that going to generate 2 to the power n minus 1 different state. So this is only necessary condition, not the sufficient condition. So this polynomial satisfying these 2 condition, necessary condition. But see, in this case, what is the meaning of this? We have to consider that x to the power 3 and x to the power 2 as an input of your XOR gate, and output of that XOR operation is considered as input to your first flip-flop. Okay, so see what this is actually. This one here, this is x to the power 1, x square, this is x cube, this is x to the power 4 flip-flop representation. Okay, so if based on this polynomial, x to the power 3 and x to the power 2 form that XOR input, these two. Okay, so here it is 1 1. This polynomial is actually satisfying our necessary condition, but it is not a LFSR that going to generate maximum possible state. Okay, see these two XOR, it will generate 1 XOR 1 is 0, that will form input feedback to this first state. Okay, in this next state 1 1 again, here it is 0, that will available here in the next clock pulse. Here it is 0, sorry, here it is 0 1. 0 1 means 0, XOR 1 means 1, that will comes here. See, so while writing or considering all the possible pattern, after 9 clock cycles, sorry, 1 2 3 4 5 6, after 8th clock cycle or in the 9th clock cycle, it's start repeating. In the next clock cycle, it will generate 1 1 means 1 XOR 1 is 0. Here it comes 0. The 0 comes here. 1, this one, okay, 0 0 1 1. This is already there here, it is already available here. So this pattern start repeating in 9th clock cycle. So this is that polynomial that's satisfying our two necessary condition, but this polynomial is not going to generate all the possible maximum number of states by this linear feedback shift register. Okay, so these are some examples for our polynomials that are going to generate that maximum number of states 2 to the power n minus 1. So that shift registers, linear feedback shift register that generate this 2 to the power n minus 1 maximum possible states, we can call it as primitive polynomials. The polynomials that generate the maximum possible states by a linear feedback shift register, we can call it as primitive polynomials. These are some examples. This is previously we have discussed this circuits, and these are external feedback. That means that XOR output is connecting with our first flip-flop input connection. Consider this as an external connection. So these are external feedback, and here we have one more possibility, that is internal feedback. What is it? Here this is that XOR operation. Inputs are output of our S or X cube and X raised to 4. These two form our input of our XOR, and its output is connected to last flip-flop's input, not to the external. So that is why this is the representation of internal feedback in a linear feedback shift register. These types of circuits are also valid. Okay, so this is the state possible in this internal feedbacking. So S and D flip-flops output we need to XOR, and its output is going to be that input of your D flip-flop, and the last flip-flop output S to the power 4th flip-flop's output is taken as an input to our first flip-flop. Okay, so this is the possible states. Here S and T value we need to XOR. That value is 0. This 0 forms input to our last flip-flop, and output of our last flip-flop is considered as input of your first flip-flop. That is the case of internal feedbacking based on this representation. Again, here S and T 1 0, 1 XOR 0 is 1. This will form our input of our fourth or last flip-flop in next clock pulse. And similarly, the T flip-flop present value, that is 1, form the input of your first flip-flop in next clock pulse. Okay, again we need to XOR these two together. XOR 1 XOR 0 is 1. This 1 form input of your last flip-flop, sorry, not here, input of your last flip-flop in next clock pulse, and the previous value of your last flip-flop form the input of your first flip-flop in the next clock pulse. So this is the case of internal feedback based on this circuit, and it will generate here how many different states? See, it will generate 15 different patterns, and after that it start repeating. So this internal feedback circuit also generate maximum possible state of 2 to the power 4 minus 1, 16 minus 1, 15 different state. So external feedbacking as well as internal feedbacking are also valid. Next type of another application is sequence generator and sequence detector circuit. Sequence generator means If we want to generate a particular sequence repeatedly, we can use the same shift register for implementing such a sequence generator. Another use sequence detector. You are given with a particular binary pattern and you have to check whether a particular specific pattern is present in that binary input or not. So we can use sequence detector. So what is the circuit for the sequence generator? This is, initially we need to set up that pattern that you are going to generate repeatedly in this register. Suppose this is the pattern that you are going to generate repeatedly, 1011. So you need to enter this value, or you need to store the value in the register in serial way or in parallel way. Somehow you have to store this value. You have to fill the value in the register first. Then take this final output feedback to first input. See, it will repeatedly generate the same pattern 1011, 1011 in every and this, see, this is not parallelly outputting, it is outputting serially. That means this is the case of serial input, serial outputting. Okay, so it will generate the same pattern after 4 clock pulse. First it generate this bit, next this bit, output this bit first, next this, and this. After the 4th clock pulse, it will repeat the same pattern. So this is that sequence generator circuit using a serial input, serial output shift register. Again, we can implement sequence detector circuit. Here it is, sequence detector circuit. Suppose you are given with a particular input pattern and you are given with a particular input specific pattern, that is 1011. You have to check whether this 1011 is available in this input serial data or not. How to perform this detection operation? See, you have to consider the first bit of your input as well as this first bit of your data or the sequence, that you have to check whether this one is available here in this pattern or not. So first bit and first bit, you have to perform XNOR operation, connect the output of this XNOR to this AND input. Similarly, bitwise XNOR operation, take the output of this XNOR and connect to this AND operation. Again, XNOR operation, connect this output to this XNOR operation, connect this output to this, and the output of this AND decide whether that particular specified pattern is available in your input sequence or not. What is that truth table for your XNOR? If both the inputs are equal, this generate 1. 0 0, it will generate 1. If these two bits are matching, then it will generate 1 and general. Okay, so if these bits are equal, then it will generate 1, otherwise it is 0, right? Then these 1 1 1 1 comes here. If all the bits are matching, see, here it is not matching, here it is matching, here it is matching, but here it is 1 and here it is 0. So this form 0, here 0 and 1, this form 0. So here it is 0 and here it is 0. Okay, so any one of the input of your AND gate equal to 0 means what will be the result? AND gate output will be 0 always. If any one of the input of your AND is 0, output become 0. So what is that conclusion? See, we can conclude that given sequence is not present, is not matching with your input stream. Okay, suppose here it is 1 and here it is 0. In that case, here XNOR become 1, here this XNOR become 1, 1, 1. That means full 4 ones as an input to your AND gate. Then in this case, here output become 1. What is the meaning of this 1? That means all that XNOR generated 1 as output. That means bitwise matching is possible at all the bit position. So this is concluding, we can conclude that that pattern is available here in this input data. Okay, so this is the case of sequence detector circuit. One more situation, that is serial adder circuit. Okay, this circuit we can use for adding. Okay, so suppose you are given with two 3-bit numbers for adding. Okay, we know that a full adder and half adder circuit, and this is that lowest bit. For adding this, we can use one half adder. Sometimes it will generate one carry. That carry will comes over here, one carry bit. So 3 bit here total. So here we need to use one full adder circuit. Again, this addition sometimes will generate carry. That carry will comes over here, and here it formed 3 bit. Here we need to use full adders. So for adding that two n bit numbers together, we need to use, suppose we need to add two n bit number in parallel, we need to use many number of full adders and half adders. So this full adder and half adder circuits are expensive. Okay, so we can perform the same operation in serial adder method, using the serial adder method, and we can reduce the number of full adder circuits required. Okay, so because these full adders and half adder circuits are expensive, so in order to perform this parallel addition, we need to use n different numbers of full adders and half adders. Right? So in order to make our circuit less expensive, we can go for the serial adder addition. How this possible? So this is the case. Here we have two numbers, one number, second number, 8-bit numbers. One can be represented using A, another using B, and that bits are given here. And here we need to use only a single full adder circuit and a D flip-flop. Okay, so we need to connect the last bit, LSB bit of our A register as an input here to your first bit of your full adder, the LSB bit of B register as input to here. And this full adder circuit will generate two outputs. We know that, sum bit and carry bit. Sum bit is feedback to your A register itself here. That means the result of this addition will store back to that same register, A register, first register. Okay. And what about carry? The carry output is considered as an input to your D flip-flop, and this output is connected back to your carry input of your full adder. What is the logic? We know that D flip-flop is delay flip-flop. Whatever value is available here at its D input side, it will propagate to your output side only after getting the clock, next clock input, right? So it will make a delay in this input propagation. That means the previous carry output value comes here only after getting next clock pulse. That is the required carry value for this full adder. Once more, the previous carry output value comes over here as a carry input of your full adder after one clock pulse. Okay, so what is the logic? Suppose you are going to add two numbers. Addition, after adding these two, it will generate some carry value. That carry value comes as an input to here only after next clock pulse. After getting this new x and y value over here, the previous carry value comes here. So it will perform the same exact expected addition and generate the result, and the result bit will feedback back to this A register bitwise, one bit after another, into the same clock pulse. This is actually a snapshot of third clock cycle. This diagram actually indicating what is that status after the third clock pulse. Okay, that is why here it is blank. That means 2-bit additions it has already done, 2-bit addition, and after the third clock pulse this is that status. Okay, so these are different applications using your shift registers: ring counter, Johnson's counter, serial feedback shift registers, sequence generator and detector circuit, and serial adder circuit. Okay, these are applications. Thank you.